Hi everyone. In today's video, I will show you how to build an AI model to find other AI models. We will use the HuggingFace API, the OpenAI API's chat model and embedding generation model, pgvector, and more exciting technologies, and we will combine everything together in an RAG, Retrieval Augmented Generation architecture. Let's first define what we want to build. There's a company called HuggingFace that hosts a lot of open source AI models. But at the time of recording this video, they have over 300,000 models. And that makes it quite difficult to decide which model is the right one for me, especially if you're not well versed in machine learning. They have a search interface where you can search by keywords and also filter by the type of model. But still, I found there's so many models that it's difficult to go through all these model readmes and figure out which one I actually want. So what we're going to build is basically a search interface. You can describe in English what kind of model you want, like I want a model that can summarize news articles, or I want a model that can translate French to English. And our application will go through HuggingFace and go through all of the models and find which models best fit your query. And since large language models are so popular nowadays, why not also use it to explain to us which model we should use? So we're going to feed all of the model readmes into a large language model, and it's going to generate an explanation and a recommendation for which model is best suited for your use case. If you want, you can skip ahead to the end of the video where I have a demo of the finished product. Or if you stick around, we can build it together. Anyways, the timestamp is in the description. So let's first explain what is Retrieval Augmented Generation and why we need it. So large language models like ChatGPT, they're really smart and useful, but they're not really up to date, and they're missing a lot of crucial information, like they don't know the details of HuggingFace models. So we need some way of feeding all of the data from HuggingFace into the LLM. HuggingFace has around 300,000 models, and if we assume each model readme is 1,000 tokens, then that's 300 million tokens. But now the problem is we can't feed all of that information into the LLM, because the context window for most LLMs today are somewhere between 8,000 and 32,000 tokens, which is a decent amount of text. Like if you print it out, it will be 50 pages or so, but it's not enough to put all of the HuggingFace into the context window. So we need a different approach. So let's say we have a query from the user, like this is what I want the model to do. We create an index from the HuggingFace readmes, and we treat it as a sort of database that we can retrieve from. So given a query, we retrieve the most relevant models to the query. Let's say we retrieve k of them. Now instead of feeding hundreds of thousands of readmes, now we only feed like 10 or 20 readmes into the LLM, and that's small enough to fit in the context window. And that's basically RAG. It's just a way of compressing a large amount of information so we can apply a LLM on it. Let's get started with building it. The first step that we need to do is get all the model readmes from HuggingFace. And it turns out that HuggingFace itself provides a free and public API to get all the models, as well as anything else that you might want from it, like the readmes, the tags, the download counts, any metadata, etc. And this is really convenient for us because now we don't have to scrape any of their web pages, we just call the API. But when you actually examine the models, you'll find that most of them are pretty obscure and are probably not that useful. At the time of recording this video, they have over 300,000 models, but only about 6,000 of them have over 1,000 downloads. So in order to not deal with any models that are really obscure, we will pick a threshold of 1,000 downloads and ignore all models below this count. So it's pretty straightforward to write a script that runs through all the HuggingFace readmes and downloads all of them. The readme data is stored in a text file, but many of them have a header file that contains a lot of numerical data that we probably don't care about, like evaluation metrics on various benchmarks. So I made some regular expressions to strip out the header and took the first 1,000 or so tokens from the rest of the readme. And we concatenate that with some data that we actually care about, like the name of the model and the number of downloads, and any tags that might be important later. And this taken together counts as a chunk that will be fed into the LLM that represents one model. By the way, if you made it this far, please do me a favor and like this video to feed the YouTube algorithm, and also Subscribe to my channel to get more video tutorials like this. The next step is to actually index the models and feed them into the LLM, and probably do some kind of prompt engineering to get a sensible output. I figured this will be a fairly straightforward task because there are many products that do a similar architecture with retrieval augmented generation. And there are a few popular libraries that claim to do this sort of thing. Two of them are LangChain and Llamaindex. These libraries serve as an intermediate layer between your code and the actual API, whether it be OpenAI or the embedding index. So I tried out Llamaindex, and indeed, I was able to get something working fairly quickly. But when I tried to customize things, that's when I started to run into problems. Like, how do I add metadata, like the number of downloads, or change the way that it's ranking based on popularity? It's not really clear how to do that from the documentation. I found that the library is relatively complex for what it does, and the documentation is spread out between several places, including the founder's Medium blog posts. It was hard for me to even figure out what it was doing by default, let alone configuring it to do something different. I am sure that what I'm doing is probably possible in this library, but after a while, I decided to start over from scratch and use plain Python to call the API directly and manage the index myself. Okay, so now that we're building it for real, which model should we use? For me, this is a question of two things: context window length and the cost. Every model has an upper bound for how many tokens you can feed into it at a time, and this is known as the context length. And also, the more tokens you feed into it, the more expensive it will cost. So we have to make an engineering trade-off between feeding it too little and not having enough information, or feeding it a lot of tokens, but then it is very expensive. Let's assume that we will have 10 models, and each model will require 1,000 tokens. So in total, we will need to feed in 10,000 tokens of context. The GPT 3.5 API has two versions, one with 4,000 tokens of context, and a second version that is more expensive, but has 16,000 tokens of context. And in this case, the 4K context model is not enough, so we will pick the 16K context model. And this will cost around 3 cents per query if we're assuming that most of the cost is from the input and not the output. The alternative is using GPT-4, which you can pass up to 32,000 tokens of context. But this model is significantly more expensive, and for the same query, it will cost 60 cents. And I decided this was too expensive for a side project. So we're going to go with GPT 3.5. One more thing that we need to use from OpenAI is the embedding model. The embedding model is what we use to take in a string and turn it into a vector of numbers. For the embedding model, OpenAI recommends just using one model called ADA002. And the pricing is a lot cheaper than the chat models at $0.0004 per 1,000 tokens, or roughly 100 times cheaper than the most basic chat model. Running the embedding model is mostly just a one-time cost that we need to do once when we index the model, so we don't need to worry too much about the pricing here. And in fact, running the embedding model on all of my data cost me around 60 cents. Okay, so now that we have chosen all of our pieces and which components to use, now let's put it together into a retrieval augmented generation paradigm. First, we need to prompt ChatGPT, and after some experimentation, I ended up with something like this. You are an AI assistant to help me find the best HuggingFace models for my task and answer any questions about them. HuggingFace is a platform that pre-trained models for various natural language processing tasks. Following will be the readmes of several models that most closely match the task description. The readmes are documents that explain the purpose, usage, and performance of the models. After showing you the readmes, I will have a chat with you to ask questions about the models and decide which model to use. Please recommend me one or more models, or tell me if none of them are suitable. You should also ask me questions about my task if it is unclear what I'm trying to do, and I will try to answer them the best as I can. Here are the readmes for several HuggingFace models. And here we will substitute this tag with the actual contents of the readmes. And finally, here is the description of my task, followed by the user input. We start by defining a function startChat that takes in a task description string as the input. First, we retrieve the model readmes that are the most similar to a task description. Next, we construct a prompt by replacing this tag with the actual text of the readmes. We then call the OpenAI chat completion endpoint using the GPT 3.5 model with 16K token context. And finally, we can retrieve the response text from the response object, and we'll just print it out for now. I'll also show you how we retrieve the most similar models given a task description. We have a function called retrieve most similar models that takes in a task description and a parameter k for how many models to retrieve. We will first call the OpenAI embedding model on the task description to get a query embedding. We will then iterate through all the models in the model index and compute the cosine similarity of the model embedding to the query embedding. We sort all of the readmes by the closest cosine similarity, and then we return the top k. And this is basically the core of the RAG algorithm. This is an extremely brute force approach because it iterates through all of the readmes, and it's probably not a good idea if you have a lot of them. We're going to optimize this later in the video using an embedding index, but for now it's good enough. How well does this retrieval algorithm work? When I tested it out, I found that most of the models that were retrieved were fairly obscure. This makes sense because most of HuggingFace's models don't have millions of downloads, and our algorithm is not really doing anything to prioritize showing models with higher number of downloads. So by default, we will usually get models that are not very popular, but it's usually the case that if a model has more downloads, it tends to be better than a model with fewer downloads. So the retrieval algorithm should probably account for model popularity in some way or another. So I decided to implement a simple reranking algorithm based on the number of downloads. This is a fairly simple formula that basically weighs the original ranking score with the number of downloads, and the hyperparameter alpha weighs the trade-off between returning more popular models versus more relevant models. To set this value of alpha, I just played around with it a little bit until I found a value that seemed to work. And after the re-ranking, we find that the top models that are retrieved tend to be more popular, and models that are very low popularity tend to not show up unless there is nothing that matches that's higher popularity. But if we prioritize popularity too much, then we just get a list of the 10 most popular models, so we have to strike a balance between the two. I'll show you some results of the entire algorithm. Here are some results for the query detect hate speech. It generated this pretty long response, and it recommended two models that look pretty relevant to the topic of detecting hate speech. Here's another example. The query here is recognize medical entities. And here, the chatbot recommends three models that are all sort of relevant. For the second model, it noticed that it's not specifically trained on medical data. And here's a third example. What if we ask the model about something it just can't do, like play Age of Empires? And it's smart enough to recognize that none of the models that were retrieved are suitable for this task, and it's good at not hallucinating anything. HuggingFace has models mostly for text, and some models are for images, but currently it does not have any models that play games, maybe in the future. I played with the model a little bit more and came up with a few observations. The first observation is GPT 3.5 works fine even if the readmes contain a lot of noise. Because if you inspect the readmes, they contain all kinds of random stuff like tables of numbers or code examples of how to call the model, random URLs, random bibliographic citations, all kinds of noise. But the model is able to pick out what is relevant and not be thrown off if there are typos or irrelevant information. And my second observation is the retrieval part is really important, because if we cannot retrieve the correct model to feed into GPT, then there is no way for it to answer the question correctly. But this is generally pretty hard because there are 6,000 models and we can only feed the readmes of about 10 models into the context. So it is quite likely that there are models somewhere in these thousands of models that are more suitable for the task, but it just did not get retrieved in these 10 models. Next, it's also hard to evaluate if we did it correctly. Like, I made a good effort to re-rank the models based on popularity, but did it really work? It's really hard to evaluate whether it worked or not. At least as far as I know, there is no good way to evaluate this sort of thing without collecting some more data from humans. But just looking at some model outputs manually, it seems good enough. So let's work on deploying it next. Alright, so right now we have everything in a single Python script. We want to deploy it so that people can use it normally, like from a browser, without too much effort. So to do this, we'll have two major pieces, a backend and a frontend. For the backend, I will use Fast API, and for the frontend, I will use a combination of front-end technologies like React, Next.js, Tailwind CSS, and a few others. But this video is not really about front-end programming, so I will leave out the details of that part. Let's start with a really simple model. So when the user starts with a request, we will send a GET request with the query encoded in the URL. And the backend will return a JSON response containing the message that is generated, as well as some other information like which are all the models that are retrieved. The backend needs to first generate some embeddings by calling the OpenAI embeddings model on the query, and then needs to do retrieval, so get the top models that match the most with the query embedding from the model index. We'll need to load the model's index from somewhere, but we can assume that it doesn't change. So for a simple V1 design, let's just pull it from S3, like a data file, and load it into the server memory when it starts up. And then once it's in memory, we don't have to touch it again. The next thing it needs to do is pass the prompt with all the readmes to OpenAI's chat endpoint, and this will give a response message, which we can send to the front end and display it to the user. By the way, if you made it this far, please do me a favor and like this video to feed the YouTube algorithm, and also subscribe to my channel to get more video tutorials like this. It took me a few days to implement the architecture that I just described, and it worked fine on my machine. However, I ran into some problems when I tried to deploy it. There are two main constraints when deploying something like this: CPU time and memory usage. The CPU usage was not really a problem because it just took a few hundred milliseconds to compute all of the cosine distances using NumPy. The real problem was the memory usage. I was running this on a Heroku instance, which has only 512 megabytes of RAM. And when I want to find all of the nearest neighbors, I have to load the entire model index as a JSON into memory. And it turns out that this was not quite enough memory, and it ended up crashing the server. The solution is to use a database, so that the data can be stored on disk somewhere, and only when it is needed, then it is read into memory. And luckily for us, there are quite a few options for vector databases, so databases specialized for hosting these type of multidimensional embeddings for machine learning. There are two dimensions when comparing these vector databases. The first is whether they're self-hosted or they're managed by someone else. Managed databases are similar to AWS or Google Cloud. They are managed by some big companies, so they are probably easier to set up. The second dimension is whether they are client-server or embedded and serverless. Most of the popular databases have a client-server architecture, like MySQL or PostgreSQL or MongoDB. They have some kind of server that stores the data, and when you want to read or write to it, you connect to the server. The alternative is an embedded database, so like SQLite, where all of the data is stored on a file on disk. And this can be potentially an easier option if you don't need to support high load and you just want to read from it from one process or something. At first, I wanted to look into some managed database options, but I couldn't find any that had reasonable pricing. They all had plans that started at least around $70 a month, even for very small projects that have occasional use. And eventually I decided on using pgvector. This is an extension to PostgreSQL, and it was nice for me because I was already using PostgreSQL in some of my other projects, so it was straightforward to add it in. pgvector has a fairly straightforward syntax where you use SQL to insert vectors and compare the nearest vectors for closest Euclidean distance. The only problem was that Heroku, the platform that I was using to host all my projects, does not support the pgvector extension. So I spent a day or so migrating everything over to render.com, which does support this extension. And after switching to pgvector, the application does not run out of memory anymore and works as expected. This is what it looks like now, and it kind of works. But the problem is you might wait for a long time for the response to generate before you can see anything. This is because when you click the button, the browser sends a request to the server, and then the server only sends back the response once it's got the entire response from OpenAI. So basically you have to wait for the whole thing to be generated before you can see even the first word. We actually have two ways to support the server sending data to the client one chunk at a time. First is SSE, and the second is WebSocket. SSE stands for Server Sent Events, and basically how it works is the client makes a request to the server, and then the server can send one chunk of data at a time to the client. WebSocket is another option, and the difference here is it allows bidirectional communication. So the client can send events to the server and the server can send events back. In this case, we don't really need bidirectional communication. We just need the server to send one token at a time. So we'll go with the more simpler SSE protocol. And this protocol is pretty straightforward. How it works is the server sends one line at a time with a JSON object, and the client will connect to the server by using the event source API. And the client registers a callback function that is called every time the server sends a chunk of data to the client. So we can take this token and display it on a screen immediately. And actually, I think this is how OpenAI implements their streaming protocol as well. So this is what the final version looks like. You can play around with it at this URL here, efficientnlp.com/modelchat. Let's say we're looking for a model that can analyze the formality of a sentence or paragraph. We just click the chat button, and the efficient NLP bot will recommend the best models for this task. And if you want, you can look at all the models that it retrieved and check out the HuggingFace pages as well. Play around with it and let me know in the comments if this is useful or not. This was a fun project, and I think it will help a lot of people find the model that they need for their projects as well. Anyway, the link is in the description. Please let me know in the comments if you have any questions. And if you haven't already, remember to like the video and subscribe, and check out my other machine learning content. Goodbye!